Happy Sunday, Honors Physics. I am recording a video to talk about the solutions for the graphing worksheets that we did in our last class. I'm going to post PDFs of these solutions onto Classroom also, so you can look at them on your own timescale, but wanted to talk about them a little bit. So you can already see the first set of answers here. The basic process for all of these graphs where there are numerical values given is to look at the slope of the position graphs and assign those slopes as the value for the velocity on the velocity graph. So in question 1a, there's two different linear sections of the position graph. The first one has a slope of positive 2, and the second section has a slope of negative 2. So what that means is that the velocity for the first 3 seconds, first half of the graph, is positive 2. So I graphed a velocity of positive 2 for those first 3 seconds. And then in the last 3 seconds, the slope is negative 2, so that means the velocity is negative 2. And so I graphed a constant velocity of negative 2 for the second half of the graph. Now I've left off the units here in my little annotations, but the units of the slope on the position graph are going to be meters per second, because you do a slope by taking a ratio of the horizontal change and the vertical change, vertical on top, horizontal on the bottom. And so the vertical change here is 6 meters if I do the entire segment, and the horizontal change is 3 seconds. So 6 meters over 3 seconds gives you 2 meters per second. If I was being really thorough, I would have included the meters per second here. So question B, I want you to notice started recording video and there's a segment missing. So the answer to part B should be exactly the same as the answer to part A. I need a line here. I'm not going to put that in right now. I'll put it in before I post the PDF though. So right away there's something kind of interesting there, because I have different position graphs and yet they're producing the exact same velocity graph. And that's because the velocity graph only tells you what the velocity is. It doesn't tell you where the object is. It tells you how the position of the object is changing, just the velocity. So it's okay to get more than one. It's okay to get the same velocity graph for multiple different position graphs. And then that same exact idea comes up in graph C. This time I gave you the velocities, so I can tell that the object has a velocity of 2 meters per second for a while, and then it has a velocity of 0 meters per second for a while. So I know the position graph needs to have a slope of 2, followed by a slope of 0. But, again, I don't know where the object actually is. I only know the way it's moving. So when I drew mine, I chose to start at a position of 2 meters, but you can choose anything you want because there's no information given to you to point you to any particular value. A lot of students choose to start at 0, and that's reasonable. You can do that, but you don't have to. You can start anywhere you want to, as long as the slopes are correct. So the correct graph doesn't have to be the exact same graph that I have drawn here, it just has to have that same shape, but it's cool if you've shifted it vertically up or down to a different starting position, because there's no contradictory info in the given graph, in the velocity graph. Whoops. Now moving down to the second set. This is basically just more of the same. I've made them a little bit more complicated or more interesting, the teacher would say. They're more interesting. But the process is the same. So I have a 0 velocity, a 2 velocity, a -1 velocity. So I have to draw slopes of 0, positive 2, negative 1. I arbitrarily decided to start at a position of 4, but you could have started at 0, it would have been fine. Could have started at, even if you started as high as 8, it would still even fit on the grid. If you decided to start at 12, you'd have to, like, I don't know, draw some extra lines on or something so that you can tell how high you're going, but it doesn't really matter. In question E, we're going from position to velocity again, so slope of 0, slope of 2, slope of 0. That means value of 0, value of 2, value of 0. And then F, slope 3, slope 2, slope 1, and that's what I drew. This time, if you don't start at position 0, then again, it's not going to like fit nicely, but it's not a big deal. It doesn't mean that your answer would be wrong. It just means that you'd have to like rescale the graph or draw an extra row of boxes or something like that. All right, this is the back side of that same sheet. The purpose of the back is to get at this idea of the area under a velocity graph and how that's related to displacements. So in this upper set of questions, the motion is uniform, and you can identify that from either graph. It's probably easier to tell from the velocity graph. It's just a horizontal line. So the velocity is constant. That means the motion is uniform. But you can tell from the position graph too. Uniform motions will always have a linear velocity or position graph, because as long as the slope of the position graph is constant, that means that the velocity is constant. And a graph with a constant slope is going to be a straight line. Could be a diagonal straight line or a flat horizontal one. That's not a very interesting motion because it has a velocity of 0. But a horizontal straight line, if you want to classify it as a motion at all, would be uniform also. So anyway, definitely uniform. How far did the object travel between time 0 and time 5? Well, at time 0, the graph says it's at 0 centimeters. And at time 5, the graph says it's at 10 centimeters. So if you go from 0 to 10, you moved 10. I think probably everybody got that right. Question C, how far did it go between 2 and 4? You have to think a little bit more now. So at time 2, the position is 4. At time 4, the position is 8. So it went from 4 to 8. That's a change of 4. All right, now we finally get to the areas. What is the area with units under the velocity graph's line between time 0 and time 5? So I'm going to use the graph itself, the black line, as like the top edge of a polygon. And then I'm going to use the axis as the bottom edge. And then I'm just going to draw vertical lines straight down to make my polygon. So this is a rectangle. It is 5 wide, goes from 0 to 5. And it is 2 high, because it goes from 0 to 2. So base times height gives me 10. And the units, notice that I'm multiplying a unit of centimeters per second times the unit of seconds. So the seconds cancel out, I'm left with centimeters. And that's exactly what I want for a displacement anyway. So I got the same answer from the area that I got from reading the original graph. And those of you who know some calculus already might be recognizing that this is talking about taking a derivative for the slope and taking an integral for the area. Integrals are a way of calculating areas under functions, and it's sort of like the inverse of doing a derivative. So when you do one of those areas, you are always going to get the change in the original function. And that applies for shortened time intervals also. If I go just from time 2 to time 4, I have this different rectangle. This time it is 2 by 2. So that gives me a product of 4. The units still come out as centimeters. And again, that answer matches what I got from just reading the position graph directly. And then the second set is accelerated, but all the same stuff applies, basically. I know that this one is accelerated from either graph. I can tell from the position graph because it has a changing slope, depending on where I look. Different slopes. And since the slope tells me the velocity, that means I know there's a changing velocity, so it has to be accelerating. But you can also tell directly from the velocity graph, because the velocity graph shows changes, so that means it's accelerating. How far did the object travel between time 0 and time 5? Okay. Well, it starts at 0, it ends at 25. If you figure out the scale for these boxes, it ends right in the middle, between 24 and 26, so went 25. How far did it travel between time 2 and time 4? Well, at time 2, the position's 4. At time 4, the position is 16. You might be realizing that this parabola I've drawn is just x squared, or t squared in this case. And then we do the areas. So for the full time interval, the area would be this triangle. Base of 5, height of 10, gives me an area 25. And for the shorter time interval, it's this purple trapezoid shape. If you wanted to, you could also break it into a square here, and then a triangle on top. But either way you calculate it, you're going to get 12 centimeters, which matches the displacement that you can get from the position graph itself. So again, the area under the velocity graph tells you the displacement. It does not tell you the position, just like we saw in the first set of graphs. Remember, I can't tell from the velocity graph where the object starts. All I can tell is how its starting and ending positions compare to each other. I can find a change, but I can't find the actual position if I'm going backwards, if I'm going from velocity to position. So, that's it for the first worksheet. The second one does not have any numbers on it, and there's a lot more curves. Oh, that's the second page. Here, this is where it starts. So the first row of graphs on the front contains all of the shapes that you see in all the rest of the worksheet. So if you get the first row correct, you can refer back to it to fill in the individual pieces on any of the other graphs. But number 1, this is linear, so it has a constant slope. It's a positive slope. That means that the velocity is a constant positive velocity. So there's no particular way to know like how high up I should make the line, because there's no scales. So I just chose something kind of in the middle when I drew a horizontal line. And then it also asks about the acceleration. Well, acceleration is based on the slope of the velocity, because acceleration is a rate of change for the velocity. This velocity doesn't change. Its rate of change is 0, so that means there's no acceleration there. Graph 2. I can see at the beginning of this graph that it's a parabola that's starting out with a 0 slope, basically. It may appear to you as if there's like a tiny positive slope at the beginning, but this is an actual parabola. It's again basically just like x squared, and so the slope at the very beginning, like the first point, has a slope of 0. So if the slope is 0, that means the velocity needs to begin also at 0. And then as time progresses, it gets steeper and steeper. It's always increasing. So the slope is always positive, which means the velocity is always positive. And at the end, it is as positive as it ever gets. This is the steepest, most positive slope on the graph. And so that means at the end of my velocity graph, it needs to have its most positive value. So 0 slope, 0 velocity, positive slope, positive velocity. All you really need to think about here is those endpoints. On the left, it's 0. On the right, it's positive. And then to evaluate the acceleration, I'm looking at the slope. This velocity graph shows a positive slope. That means the acceleration is positive. All right, graph 3. This one again starts with a slope of 0. It's not in the same place. The position obviously isn't 0. But the slope of the graph is 0. So the object is not really moving at the beginning. So my velocity graph also starts at 0. Over time, the velocity, or the slope, becomes negative, and it gets more and more negative, and at the end it's really negative. So my velocity needs to become negative, get more and more negative, and end negative. So again, just thinking about the endpoints. 0 slope, 0 value. Negative slope, negative value. Sometimes I suggest to students that they just kind of make dots. So instead of drawing in the line the way I've done it, you could start by saying, well, that's 0. Put a dot right on the origin. And then over here you could say, well, that's negative. So then you put a dot down in the negative somewhere, and then just connect your dots. This time the acceleration is negative, and I can tell because the velocity is a decreasing function. There's a negative slope, so negative acceleration. Number 4. This time the slope is initially negative. It's already decreasing, even at time 0. So if there's a negative slope here, that means the velocity has to be negative. So I started it below the axis. But by the end of the graph, the slope has become 0. So that means that the velocity has become 0. So the end of my velocity graph needs to be right on the axis to represent a 0 value. So very negative, 0, 0. I can see this time that the velocity graph has a positive slope. That means the acceleration is positive. And then number 5, I'm going to do this one a little quicker. At the beginning, it is a positive slope, so that means the velocity is positive. So I would start up here someplace, positive velocity. And at the end, the slope is 0, so it means I have to end with a 0 of velocity. So I could put a mark there, connect them. Oops, sorry. I went to the next page by accident. Positive, 0, positive, 0. Again, the velocity graph is like a graph of the slopes from the position graph. This velocity graph is decreasing as a negative slope, therefore the acceleration is negative. So again, all of the other graphs are just sort of Frankensteined together from these 5 basic graphs. So I'm going to talk through these ones much faster. I don't want to take a huge amount of time for this. I have a feeling the video is already like 20 minutes long at this point. So number 6. This has a 0 slope the whole way until the middle of the time interval. So that means that the velocity is 0 for the first half of the graph. So that's what I've done. Constant 0 velocity. In the second half, the velocity changes. It still is at 0 at this midpoint, but by the end of the graph it's positive. So that means I need my velocity to change from where it was to something positive. The accelerations in the first half is 0, because the slope of the v graph is 0. In the second half, the v graph has a positive slope. That means the acceleration is positive. 7. This time the first half is curved, and the second half is linear. I begin with a 0 slope, I end with a positive slope. So 0 velocity to positive velocity. And then from the midpoint until the end of the graph, I have this straight line with a constant slope. That means the velocity is constant. So the positive velocity that I finished the first part with, I'm just going to keep that positive velocity all the rest of the time. So the velocity graph shows that. It was increasing, but once I reach the midpoint, it just sticks with that value the rest of the time. So constant positive velocity. So the initial acceleration is positive, second acceleration is 0. This time I begin with a positive and constant slope. So there's a positive and constant velocity. And then that slope gradually diminishes, becomes more gentle, closer to 0, and ends with a 0 slope. So that means the velocity has to end at 0. Velocity decreases from its initial positive value towards 0. 0 slope, 0 acceleration, negative slope, negative acceleration. So that same general interpretation applies for all the rest of them. And don't want to talk through every single one of them. Let me see if there's any that are oddballs that I think need an extra explanation on. Number 5 on the back. This is a specific case that you're going to see many, many times. This is basically like the motion of an object that you throw straight up in the air, and then it goes up some height, stops, falls back down again. When you throw things in the air, they follow a parabolic path, just like this. So it's like I've thrown something up, reaches a maximum height, comes back down, and like I catch it again. So in a case like that, I have a positive velocity at the beginning, because I released it to go up. Eventually it hits its highest point, and at the highest point it has a 0 velocity, because it's not going up anymore, but it's not coming down yet. And then as it falls, the velocity is negative, and it gets more and more negative, like this. So the velocity graph has this just a single straight line that decreases from a positive value through 0 to a negative value. And so, because the velocity graph is just a single line with a constant slope, it's just a single constant acceleration. And on Earth, that acceleration would be with a magnitude of 9.8 meters per second squared, like we saw a week or two back. But it's that same acceleration all the time. It has that acceleration on the way up, it has that acceleration at the top, and it has that acceleration on the way down too. And the other one that's a little bit odd, I don't know. I feel like I often get questions on this one. This one is weird because the parabola in most of them, in most of these problems, if I gave you a parabola that started out already with a non-zero slope, I usually end it with a 0 slope, but this time I cut it off before it got the whole way to 0. So the velocity is negative at the beginning because there's this negative slope. And the slope is getting more gentle. It's approaching 0. but it doesn't get the whole way to 0. So instead of having this line go the whole way to the axis, it needs to stop changing while it's still negative. And then in the linear section, I just keep that negative velocity going. But I think that's it. I've talked enough. If you want to ask me any specific questions about any of the ones that I didn't go in detail over, feel free, please talk to me about them. Like either during office hours on Monday or during class on Tuesday or Wednesday, depending on which day you've got me. But I think that the ones that I talked about in detail probably good enough. So I'm going to sign off and go do some other stuff.